Hey, welcome again, Physics 102 students. I'm not sure I would call this a second question because a couple people asked about number 24, but really they're asking about it because sadly the problem was not complete and there's a little confusion at the end. So let me add what the rest of it says. But I thought, hey, why not make a solution? I'll treat it like it is a question. And so I'm going to read it here. It says, a rock is dropped into an abandoned mine. And so let me just kind of make an abandoned mine. And so here's kind of this mine shaft going down. And somebody stands up at top. And maybe they've got this little rock and they're going to drop it. Okay. And a splash is heard 4 seconds later. And so a lot of these old abandoned mines will fill up with water. And so maybe that's what the person's going to see. Hey, do I hear a splash? So they drop it. The rock hits the water, makes a splash, sound comes back up. And all of this takes a time of 4 seconds. So far good. So far so good with the problem. It says, assuming that it takes a negligible amount of time for the sound to travel up the mine shaft. Okay, so really we could just say it took 4 seconds to drop. But the sound's pretty quick. It does take a little bit of time to go up, but they're saying, okay, ignore that. So that simplifies the problem a little bit. We don't have to worry about the speed of sound. It's just really the falling rock. And that's what this chapter is about acceleration and velocity and speed, and that important difference between average and instantaneous velocity. Okay, so again, I'm going to keep reading. Let's see, where was I? Assume that it takes a negligible amount of time for the sound to travel up the mine shaft. Determine the depth of the mine shaft. So that's one question. We'll call it D. What is the depth of the mine shaft? And then how fast is the rock? And so V, velocity. It's the second question. How fast the rock is falling when, and this is where the question ends, but it should say when the rock hits the water. Okay, and so how far did it travel, and then what's the speed of the rock when it hits the water? So that's the missing piece here. And there's, again, a couple of ways we could do this. I'm going to go in reverse order here and look at velocity. The velocity, and again, instantaneous velocity, we said, would be then something that looks like the following. If you remember our discussion about acceleration, maybe I'll drop that here for a second. Why don't I put the equation for acceleration? It's change in velocity over time taken. And since we're dropping it, we know the acceleration is 9.8. We know the time is 4 seconds. And then this would be final speed minus initial speed. And this is instantaneous speed. And I think that's what they're asking. They maybe could have been a little more clear when they say how fast. No, I think how fast when it hits the water is a good way to say, hey, you need to realize we're asking for instantaneous. So that's a good phrase. And of course, we drop it, so they're saying the initial speed is 0. So let me bring the 4 seconds over to the other side. Let me put the 9.8 meters per second squared for the acceleration. Let me put just final speed and then minus the 0 that I just mentioned. And so the final speed is the speed when it hits the water. You could put a 10 here and just go 10 times 4 and get 40. Nothing wrong with that. I suppose a little more accurate is to take the 9.8 and go times 4. So that would be 39.2 meters per second. But either one is fine, okay? And so that is one of the answers. Now, the other answer here is how much distance. And again, we really have two ways we could approach that. We could say distance equals, and there's the important step, average speed times time. Or we did learn that in the case where you start from rest, but only the case when you start from rest, distance equals 1/2 acceleration times time. And so either one works great. Maybe I'll do this one first. This is a 1/2. This would be 9.8 meters per second squared. And the time is the 4 seconds and squared. And so if we look at the units, we got a second squared. And remember that from your, I guess, math class, if you have something that looks like xy and you square it, it means x is squared and the y is squared. So this would mean the 4 is squared, making a 16, but it would also mean the seconds is squared, which is why it cancels with the seconds squared from the 9.8 and then the 1/2. So if I grab my calculator here, and I'm going to have a 1/2 times a 9.8 times a 16, and this would be the 78.4 meters. And 10 is fine here. So just as well, we could do something like this, and I'll go 1/2 times 16, that's 8. 8, and if we call that a 10, it would give us an 80. So 80 meters is fine, and so is 78.8. I would say this is a little more accurate in terms of the number, but this shows me, you know, the concept, and so that's fine. I'm good with that. Of course, as I mentioned, we could have done it this way. This is how I did a few of them in class. And if you come back here to your average speed, and this might be the one to do it. Again, either one's fine. But we know we dropped it, so our average speed would be the middle of the two. So halfway between the drop, 0, and the final speed of 40 is 20 meters per second for 4 seconds. So 20 times 4 is 80 meters. So there would be matching that distance. And if you also wanted to do the average of this speed, you could take, all right, 0 and average it to the 39.2 and divide that by 2. So there would be the average speed. And if you multiplied that by 4, you get, of course, the 78.8 meters. So that works too. So you can either use the 10 for acceleration of 9 or 9.8. I don't really care one way or the other. Like I said, 9.8 might be a little more accurate, but the 10 shows me your thinking, and that's what we're after. And then, like I said, in this case, you can use either one. I do this one a lot. I kind of prefer it because this one's limited to the fact that you have to start with a 0 speed. And that's the case in this problem, so it works. But sometimes, if I use this too much, I've noticed that students then start to use it when the initial speed is not 0, and that's when they get into trouble. Whereas if I use this one's true no matter what your initial speed is. Because to get your average speed, you're always going to take your beginning and add it to your end and divide it by 2. So that's how I got the 20. So hope that helps. All right. Bye now.